Okay, so in this video clip, we're going to take a look at Lending Club, which historically was a peer-to-peer lender and had an online platform where lenders and borrowers could meet and source financing, advance financing. More recently, Lending Club has become, I think, more like a conventional bank with a fast processing for loan applications, and the peer-to-peer platform is gone. Yes, if we go on to Kaggle, we have very rich data sets. All Lending Club data set, I think, is the biggest one that's sitting there. And we have, and this is Nathan George, who scraped the data and managed to get the data. So that involved a bit of work to set up and execute, and looks like at least a gigabyte there. If we come down, we don't have the headings, but a very something like over 1 million rows of data and of different loan applications, and also in Kaggle, which is very nice. We have code artifacts that can be used for processing that data. Right, so normally I go by the most votes and dip in to take a look at the work that people have done, and like some really nice data analysis going on, where we're doing exploratory data analysis, uh, data pre-processing, normalizing data, and then the model building. That very often is the type of approach people use. This is a good one from, I think it's Robert, from Joe Corliss. It's a little bit dated 6 years ago, so I presume going up to 2018. And again, why I'm attracted to this specific notebook just relates to the certain neatness in the way he presented the data. So we have 150 rows of data, maybe close to 1 million. Maybe at this juncture it was less than 1 million applicants, and then quite a bit of analysis around how much of your data is missing or incomplete. And if we toggle down a little bit further, we'll see some neat graphs that are set out here in terms of the loan amount that an individual applicant would have received. I think the maximum typically is $40,000. And then we're looking at charged off and fully paid. So we're trying to predict. The object of most of the modeling here very often is to try and predict default on the loans, which is incredibly expensive for banks when they lend out funds. You're very often the big cost is default or late payments, and then a question of, well, how much money do you recover on the basis of what people paid back? And typically loans are 5 years or 3 years, so 36 months or 60 months. Most, I think, were 36 months. So just two maturities. So a cost to the business obviously is default, but then where in the loan process was it? Year one, year two? Was it month 26 when the default occurred? If it was, then you would have received quite a number of installments. Now, the big issue around this data is just the scale, right? And we might prefer to go for, if it's a research project, we would use the full data set. For maybe class, school project, master's project, you would use a toy data set. But if you wanted to use this specific data set with code artifact, you can go into a very nice feature on Kaggle is you can open in Google Notebooks or Colab. So the full data set can be brought in. So we can access the data actually using the first cell here. But an issue that arises is that it's not instant. So very often we find that when we try to bring the data into our project, it's just the sheer scale of that gigabyte. Now, when we run this code here, it's downloading the data, but not to our own machine. It's downloading it to a space where Kaggle can access or where Colab can access the data, but it doesn't come onto our machine. So in that respect, this is nice, but it's going to be cumbersome in the sense that it just absorbs a lot of memory to download and to read in the data. So that's a bit of a problem. Fortunately, if you look up it's Joe's profile, there is a GitHub link. So Joe Corliss does have a GitHub account. Maybe we'll go there first. And he's done some interesting profile and some interesting projects, but the Lending Club one is there too. So if you go into the IPYNB notebook here, we can sort of see the end product, right? So we can see the inputs and the outputs. So we see the code cells and the output from the code cells. And all the graphs that are generated in the Colab have been replicated here in GitHub. So it's a nice check. And the plot, the helper function, or user-defined function that's developed here is used to develop these type of plots. And so very often what we're trying to do is look at a particular column of data, the loan amount, for instance, how significant is that in influencing the payoff, right? So fully charged, so charge off would be where you default, or fully paid is where the loan was paid in full. So you're trying to make comparisons and look at in this pivot table that's generated by the pandas command group by, you can see that there's this people who pay off on average have slightly less borrowings than people who default. But that's a very specific, obviously we would have to drill down into this even more to define maybe the instances where that's occurring. Again, the term, which would be the maturity on the loan, does that have any overall bearing? And again, it goes through that analysis here. So in the in the pivot table that's developed using the group by command from pandas, people who borrow for 36 months, 16% chance of non-payment, but those who borrow for 60, there was 33. Again, you have to, these are very prima facie type results, and we'd have to drill down further, but it's sort of interesting. And again, if I go back to Colab, where I'm running the exercise here, it took a little while to download the data. So it's 1 minute. I suspect it was a little bit longer than 1 minute, in fact. And then to read in the data, well, we would initially import in the different libraries. And then to read in, to get the data from and create a data object. So read the CSV file that was downloaded, and then read it in as a data object into our environment. Now it's not coming from the content folder. So we go into the content folder, we won't see that 1 gigabyte of that data is not there, right? The loan data is not there, but to make it available in this environment, we can read it in to our Colab. But again, the issue is the scale of the data is just a little bit bigger, and great for doing research because we have a huge amount of data to mine. In fact, it turns out there's 1.6 million rows of data and 150 columns of data, and the size of the data set was found to be 1.8 gigabytes. So, fairly significant amount of content. Very often the problem we deal with is we don't have enough data, But here we can see we have a lot of data, and we can use the GitHub, the Kaggle notebook developed by Joe Carlis to analyze the data. And it's great, right? So these are loans that are still outstanding, yet to be paid. Joe would have developed this, I think, in 2018. So the peer-to-peer platform is still fully operational. Of that fully paid, 646,000. And those on the charge off 168, and then some people in distress. So if we go current would mean it's unclear if they're going to default or fully pay. Loans are still live, right? But historic data would have suggested the bulk of people pay off their loans on Lending Club, and a proportion didn't, right? And some of these other categories are also states of default, right? So we bifurcate our loans just so that we have fully paid and charge off. And then the loan shape changes dramatically in that now we've pared down our data sets to 814,000 rows and 150 columns. And I suppose we can keep doing that. And, we end up in a situation where that bifurcation is 79% of people paid, but 20%, 80%, roughly 80% paid their loans fully, but 20% didn't. So essentially what the Lending Club have here is a very complete data set and a lot of scope here for cleaning our data and so on. But when we get down to the modeling, it would be time consuming, right? And if you're developing maybe a research project for masters or school project, to get your head around, given the size of the data set, perhaps one way you could approach the analysis here is to use John Hold's. So I'm going to take a look at John C. Hold's webpage because he has a textbook developed. So Machine Learning for Business. So if we look at the range of books John has here, some are really very substantial in terms of usage in particular areas in the finance space, derivatives and risk management, financial institutions. These are leading textbooks used by professional bodies like CFA and FRM, Financial Risk Management. They make heavy use of these textbooks. In fact, kind of a Bible. And I think John has created sort of a Bible here for machine learning although it's business, so it is business textbook for students in the finance space. I think they would find this also very useful. And John has some PowerPoint slides, right? And we can take a look at those. And also he has material set out based on chapters. And chapter 3, he looks at Lending Club, and he sets up if you like, a toy data set that is more easy to work with for just smaller projects where we're not doing, let's say, dissertation scale type assessments, or just to get your head around the type of analysis and to scale back the data with a toy data set and make use of logistic regression, which is the key model that's been developed here. So we can take a look at that. Okay, so that's the HTML file. We might download John's file here and the data sets and the definitions. So there is a set of definitions here that he provides. And also we have PowerPoint as well. So Couldn't open file. Okay, so it's probably something my end, right? Because that file was opening without any issue before. Let's take a look at the slides here. So I'll just go into chapter 3 to map out what he's done in Lending Club. So the first section is linear regression for the Ames house price data set, and he goes through OLS and ridge regression, lasso, elastic net. And then in the second part here, logistic regression, and how logistic regression is used to predict binary outcomes of a 1 or 0, and the sigmoid function that's based on this mathematical expression. And then he uses not gradient descent here, he uses a maximum likelihood, which is a fairly standard way to operationalize logistic regression. And then he sets out what he has in his data set. So he strips back data set to home ownership, which is just rent versus own, income of the applicant, debt to income and credit score. And then on the basis of these independent variables, he tries to predict default. Where in his data set, he has 12,290 observations, 9,733 were good, 2,557 were charged off or defaulted. That's roughly the same proportions, about 20% or so, a little bit higher, I guess. 7,000 loans were for training, 3,000 validation, 2,290 for the test set. And then this is what his data would look like. So you're trying to predict 1 is for a good loan and 0 is for default. And 1 owns their property, 0 rents. But owns might be sort of an interesting one in that if you had a trailer, do you own your own home, right? So some of the values we get here may not be as compelling as we might expect. We'll see that in a moment when we look at the output from the logistic regression. And so if you run the logistic regression, these are the parameter estimates you would obtain. We'll check that in a moment. And then John goes through setting out for different threshold levels what the impact is on the confusion matrix, where we have true positives, false positives, true negatives, false negatives. And we'll see that in a moment. Some definitions are provided in terms of the F-score, precision, false positive rate, true negatives, true positives, and accuracy. And what I appreciate very much going through John's notes is everything that he's developed here, he also has managed to set up in Excel. So, okay, so what I'll do, I'll go through the basic analysis. I'll show you how we can obtain John's notebook, IPYN, so this file. So let's go into downloads and let's look at downloads and then look at our logistic. So let's extract that. We'll just extract all. And then you can see in our downloads, if we go into our file, we have this file here. Okay, so if I want to implement John's analysis that he set out in the textbook for Lending Club, I create a new instance of now you need to be signed into your Google account. I'm signed in right here. And then I open up Colab. And then I go to Colab, open Colab. And then I upload the file that I've taken from John's portal, keeping in mind it's in this folder here that I extracted. So I opened that up directly. And then I can straight away start to run the code. Now, if I execute the first cell, which is just basically bringing in, let's close this one down. So I'm just bringing in some libraries from sklearn, pandas, numpy for multi-dimensional array mathematical operations, pandas for data transformation, seaborn, matplotlib for graphing, and then the sklearn for machine learning. And we have a specific interest in logistic regression. Okay, so if I run this next cell, we're going to have issues because we don't have the data. Right, so the data, we're looking for lending club, train data, validation data, test data, but that's on the portal. So if I go back to John's web page here, I can download not the full data set, it's the training, validation, and test. So 1, 2, 3. Then go into my content folder and upload, and then I look for where those files have come in, right? 1, 2, and 3. So let's open those up. Okay, now when you close down your project, your Google Colab, those files will no longer be there. Again, if I run, it still won't work. The issue here is the name doesn't match. So we just change the name to reflect what's in the code, right? That's the simplest. So I just rename. So because I download these files a couple of times already, we'll see that every time I download, we have a new instance. So I need to rename the file so it reflects what's in the code artifact that John has provided us with. Okay, so let's run that. And the code has come in, and John has made clear 1 means the loan was good, paid in full. 0, we had a default. We have home ownership, income, debt to income, FICO, which is a credit score, and loan status. 1 if the loan is good, 0 if the loan defaulted. Okay, so again, the data has already been split into training, validation, test set. There are 7,000 instances of the training set, 3,000 from validation, 2,290 instances from the test. So this is consistent with what John has in his PowerPoint, right? And it's also consistent with an Excel version here. Okay, so when we run this code here, we're getting an issue, but that's normally easily resolved. It's just access equal to 1. And if this doesn't work, I just go to ChatGPT or go to Gemini AI and see if they can come up with a solution. So if you get an error, right, a good way of dealing with that is perhaps use Gemini, which last couple of days hasn't been responsive. So let's just see if that works. Okay, that seems to have resolved our issue here. So really what we're doing is we're splitting the data into what we're trying to predict. We're trying to predict the loan status, and then we're separating out as the independent variables. So this is the dependent variable. This is what I want to predict. Did the individual pay in full or default? And then link that back to the FICO score, debt to income, and home ownership. Okay, so we print out the different data sets that are here, just the first 5 rows, just proof that they're there. And this next section then is doing a few things, but I suppose the key thing is it's splitting the X's from the Y's. So we've X train, X validation, X test, and then we have the Y's as well. And I'm normalizing or standardizing the data. So to sort of understand what's going on in the cell, again, I haven't seen this before with other textbooks, and I think it's a real strength of John's approach here. But if I go into the Excel file, Excel Logistic Regression, and check out what's in the downloads. So it's Lending Club. It's this one. The manual working out in Excel provides the backdrop to what's happening in the IPYNB file. So what we have here basically is we've separated out. So this is following in parallel to what's happening in the IPYNB. It's the same data set. We still have that number 12,300 rows or so, right? Or 12,290, whatever it is. It's the same data set as what we have in the Python notebook, what we've loaded in. And we are predicting whether the loan defaulted or was fully paid. So 0 here means defaulted, 1 means fully paid. And then we're using our we're using these x variables to predict as dependent variables to predict the y variable, right? So then the original data here is we're taking, if you like, okay, so let's start editing the file. Okay. And so what we have is our original data set, right? So this is the charge off, and this is the original data. And we take the mean of just the training data, 7,000 rows of training data, and we take the average. And again here for annual income, and again here for debt to income, and then here for the FICO score. Then to normalize the raw data into data that is scaled, we take the mean value in each instance and subtract from the actual, and then divide by the standard deviation. So in fact, what we get here is our data, the mean, let's take it over here, the actual minus the mean divided by the standard deviation. Okay, now the fact that it's set up in Excel, it's color-coded when you highlight the formula cell, allows you to trace through exactly step by step what's going on in terms of the setting up of the logistic regression. So we are predicting here in our model, what we're doing is this Y value here, if you like, is being generated by what we saw in our PowerPoint. So we're generating, using this, we're making prediction, a probability. And that's being cast. We're using by taking the exponential of that, right? Taking, so the sum product, if we just highlight, maybe I could zoom out for a second. Right, so just taking that value there, double clicking. We're taking each of these weights and multiplying respectively by the actual scale data. And then we're adding the constant. And then to calculate the probability, it's e to the power of, so 1 over 1 plus e to the power of that y value. And then from there, we estimate the log likelihood. And then the weights, if we go into data here, we can see if we invoke the solver function, we can see we're taking these cells, we're trying to minimize the log likelihood. We're trying to, so the cost, let's just see that for a second. So to estimate, to optimize the weights, he uses solver. And then he's saying, look, by changing H7 to L7, we might be able to see that, H7 to L7, we're trying to minimize the cost function, which is N6. N6 is the cost function, which is the sum of the likelihoods that are estimated using this function. And to understand this function, we're using the approach set out here. Excuse me. So the maximum, we're minimizing the cost function by maximizing the log likelihood. So we're maximizing probability by minimizing the cost. And we're doing that for the training data to optimize the weights, but this is just for the training data. Okay, so in terms of what is initially set out is for the training data, and then we test it using the validation and the test data as well. So these steps that are set out here manually in Excel, we replicate, and the construction of the ROC AUC is also manually developed based on in Excel, and the results we obtain here manually mirror the results we get in the Python notebook. So let's go back into the Python notebook again, Lending Club. This is John's. Okay, so when we observe here the frequency of default, roughly 80% are paying in full, 20% defaulting, but some would pay maybe halfway through or three-quarter ways through before defaulting. To invoke logistic regression in this Python notebook, we're using an sklearn, the sklearn library. So, and we're training the data in the same way. So we're taking this training data to parameterize our model. And the parameter outputs we're obtaining here are consistent. If we check here, these are consistent with what we get in John's optimized using solver. The weights here that are produced are consistent if we go back in and look at John's. I just put here above. I can just paste in Control V and come down, and we'll see the results obtained here from Excel are consistent with what John managed to obtain in the Python notebook, which is, again, it's nice that everything aligns, but it's also what's key here is that the Excel, the traceability that we obtain by using Excel is mirrored here in the Python notebook. And we can use, it's not the full Lending Club dataset, but it's a toy dataset that's very easy to manipulate and work with and extremely good for projects and even as a pilot for a deeper research into Lending Club, just to test out the ideas. Now, again, what was going on in terms of the standardization and the scaling, we're taking for the test data, we're taking the mean of the training data dividing by the mean of the standard deviation for each variable. And likewise, then for each iteration of the training data for the independent variables. Okay, and again, John doesn't invoke here sklearn. He uses the same approach for a maximum likelihood approach that he's written up sort of in manual code. We'll see in a moment how we can do this using sklearn. And then he prints off the cost function. And again, we can replicate if we go into looking at the cost function here. Maybe I'll take this one and copy. And if we copy the results into what's here, we'll see John managed to replicate the same results again. So the cost function for the training set on par, same again, same again. So the manual estimation performed in Excel, John has managed to replicate that using a customized code that he's developed in his Python notebook. Again, so when you look at this code initially, it's not terribly intuitive, but with the benefit of the Excel supplied by John, it reveals itself. And that's a remarkable feature of the approach used by John, right? And then what's interesting here, if we look at the output here from the charge off, right? So 80% of people will pay off the loan, 20% default. But if I created just a naive estimator that said, okay, I want to predict what's going to happen based on the economic data that's provided, a very simple naive approach would be to say, make a prediction that everybody's going to pay off the loan. So if I'm developing a model and I just naively point to everybody, if the model just says everyone is going to pay off, then basically 80% of the time I'm going to be correct. And so one way of addressing this, and especially this is true for financial institutions, the big cost is when a mistake is made and somebody doesn't pay. So the losses, if you can avoid a loss or have an early detection system or anomalies that can be instrumentalized and pointed out and flagged early on, being able to avoid those features that lead to default or correlated or consistent with default, then that would be better, right? So, but the model itself, if we take the data, the raw data as provided here, while 80% of the time, if the model just throws out a 1 as a prediction, it's going to be correct 80% of the time. So it's a little bit of a fallacy when we get 80% accuracy. So John maps out here, okay, rather than having an analyst must decide on a criterion for predicting loan will be good or default. This involves specifying a threshold. By default, this threshold is set to 0.5. So in most software, if the value we predict from the model is greater than 0.5, then we treat that as a 1, that the individual paid off, otherwise 0. But that's a problem here because most of the time we're going to get in excess of 0.5. And so if we don't do anything else, right, most of the time the model will just predict default, loan fully paid off, should I say. So the way we deal with that is consider different thresholds, adjusting, moving away from the normal 0.5 setting to saying 0.75, 0.8, 0.85, and setting out those thresholds. And then building confusion matrices based on the information provided. And this is the output that we get. So what we typically find as we increase the threshold level, the level of accuracy declines, but we are identifying more true positives. So just to see that again, go back to John's PowerPoint notes. Here, what we're seeing, if we can get back to, so for the 0.75, these are the confusion matrices that are produced. And so we're trying to predict, it's very important for us to predict correctly defaults. But if we correctly predict defaults, a lot of the time we're going to actually refuse mortgages on the basis of the model is just too onerous, right? So there is an issue here. At what level do we pitch this SAD? And the trade-off in managing the thresholds is very much related to the statistics that are reported here and to the ROC curve, AUC. So we're looking at, for different Z criteria, the ROC curve maps out the trade-off that as we must accept to get more true positives, we're going to have to get more false positives as well, right? So we can predict every default by pushing up the false positive rate, which has a cost to business as well, right? Now, to see how the ROC curve is produced, John also has produced a full working, so the manual mapping out of the ROC curve and how that is affected is all parallelized here in the Excel spreadsheet. Again, I think for students, that's a really neat way that we can see how all that works and understand fully what the ROC AUC is providing in terms of a metric for analysts. Okay. Now, going back again, right? So I want to take a look again, a deeper look here at the outputs. Let's just see, can we generate the ROC curve? We can. Okay, and that's all done manually based on John's code. Okay, so I will include this link below the video clip, and I'll also provide you with an additional video clip, a link to another collab I've developed where I bring in, so just for, we'll upload, I want to upload, go into the content folder here and upload my files again. In fact, I think if I go into desktop, John data, I have clean data here. So I'll just load in this data. And we can run the cells again. So just make sure that the file, we have our content folder. Yeah. So open up our content folder and just make sure the data's gone in. I'll try that again. Upload. All three files again. And we can import in our libraries. Same as before, exactly everything is the same, but I've introduced the modifications, axis and the percentage and then the logistic regression. And I follow up, I use stats model also to verify the results. We did that in Excel already, but stats model gives a nice overview. It gives a pseudo R squared, which we don't have in Excel. It's low, right? But the variables are statistically significant, except income. And maybe that's been captured here anyway by debt to income. Okay. And so I think I just improved this. Again, it might be worth noting if I put in 0.5 here into John's vector for thresholds, I can expect I'll get 4 confusion matrices. So now I have 4, and you can see we're that 79, 21, and 80% and 20%. These are basically zeros. They are sitting here, right? And I have a third collab link, and I'll share that in the below the video clip. Again, I'll load in as before. I will load in the data. So upload those 3 files that John provided us with from his. And what I'm doing here is automating a little bit some of the manual workings. So I'm taking John's Python notebook as the centerpiece and then I'm modifying the notebook to take into account the more kind of automated sklearn approach. So that's our logistic regression output, which we're happy with. It matches the results from Excel, and we're replicating here. If we just inspect the results, you can see what's obtained here in terms of the estimation. We replicate using stats model. So this is from sklearn, this is from stats model. Both results tally, but the benefit is I get those z-scores and p-values, right? Let's close that down. And then in addition, same as before, I put in here 0.5. So you'll see the model will just predict always pay off, and you'll get 80% accuracy. And then I adjusted the threshold for full numbers. So I just made a slight tweak on John's to remove that. And I ran this again. So display, so I need to, it's a library that I'm missing. I think it's one of these, confusion matrix. Let's just run this. And come back. Try again. Okay, now it's worked. And so we have something that looks a little bit more like for our confusion matrix, right? So we values here. So it's if we add, I think it's for the validation set, if I remember correctly. Oh, the test. So it's the test against prediction. So in the test, 2,290. And if you add the quadrants here, we're getting the values for the confusion matrix. And also I have to be a little bit careful that the confusion matrix that we produce here are consistent with the design set out in the, yeah, I think these are more consistent with, we go into our, yeah, so if we look at John's confusion matrices, so the true negatives and the true positives. So what's on the diagonal is where the model predicts correctly. Off diagonal, the model in predicting incorrectly. And I think we have, this is the predict default and predict no default. So the bulk of our, if we go, so this is when we predict that there's no default and it's true. And if we had 0.5 here, basically 80% is here and here. Let's check again with the results. Come down. A little bit further down. I think maybe I have to, okay, reverse order of matrix. In fact, this is the way I have to do it. Logistic regression. So we're using logistic regression, decision tree, random forest, and gradient boost. And now the shape that I have here, because I've reversed the order of the matrix, the values that I'm obtaining here and the interpretation of the confusion matrix is consistent with what's in John's PowerPoint notes. Right, and let's see, grid search, hyperparameter tuning. That I'm going to leave that out for the moment. I think it was taking a little bit long, and it wasn't lightweight. It was back to being cumbersome. But to get slightly better improvement, we could also we could tune the parameters better. Okay, so I think I'll leave it there. My feel here is that Lending Club is a really great data set. The downside is scale. If you're a newbie in the data finance, in the data area, proof of concept is very well established on the portal here that John has set up. The textbook is a fabulous textbook. It's very well written. The approach is not technical in nature, very much where possible. There's an Excel example provided. It parallelizes what's happening in the Python code. And I think it's sometimes the Python code can be inscrutable, especially people trying to pilot an idea, but if you see it in Excel, it reveals itself very quickly and it's very intuitive. So that's one of the great strengths of John's textbook. Most of the data sets here are relatively small. The one exception, I think, is for the Black-Scholes model, where you have quite a few data points, and I think the development of this part of the textbook follows, especially these two, John's own papers, which is cutting-edge type machine learning introduced into the finance arena. Okay, let's leave the analysis there for the moment.